So today we're going to be focusing on the paper 5 question 1, right? I'm going to be explaining in depth what that is, right? The different parts that come in this question. And this is a video series. There are 5 videos lined up just for question 1, and my goal is by the end of this series you should be able to understand how this question can be better answered, right? To start off, this question consists always of two variables, right? The goal is for you to analyze and present a method in which an experiment can be conducted, right? So it consists of two variables. A variable is basically anything that you can change, right? If you scroll down and you look at your paper 5, you're going to see 5 things, right? Procedure to be followed, measurements to be taken, control variables, analysis of data, and any safety precautions are to be taken. And how this is going to be categorized is that in an exam situation, you don't really have to categorize it and say procedure, measurements, control variables, all of that. There's a particular format that I would highly encourage that you follow that we're going to cover in this video. So the first one that you're going to write is defining the problem, right? Remember, you're sort of trying to put yourself in the shoes of an examiner and structure an experiment that someone can be able to conduct. So the first one is defining the problem. And under this subtopic, you must include 3 things, right? Marks. Well, it usually consists of 2 marks, right? In most instances. But you must include 3 things in order to get those 2 marks. What are they? Number 1, you must list independent variable, right? So under defining the problem, which is the first subtopic that you write for question 1, you must understand what an independent variable actually is. So an independent variable is basically a variable or any physical quantity whose values can change. So that's what a variable is. But an independent variable is one that you deliberately change in an experiment, right? It is the vector that you vary and you observe how it affects another variable, right? For example, I give you a student who investigates how the speed v of a trolley at a distance d from the initial position varies with the mass m, right? So the speed in which a trolley moves, how does it vary with the position and with the mass m, right? So I gave you a student who's trying to figure out how the speed v of the trolley varies with the mass m, right? The mass of whatever will be causing that thing to move, right? So in this question, if you want to identify the independent variable, you can easily see that you can't deliberately change the speed. You can't do that, right? It's a consequence of changing the mass. By changing the mass that's pulling the trolley, you can be able to change the speed. So you can see that the independent variable is the mass. You can deliberately change that. And that becomes your independent variable, right? Move on to the next one is the dependent variable, right? It is the one then that you measure in response to the change in the independent variable, right? It depends on how the independent variable has been altered. So if you change the independent variable, the dependent variable changes as a result. So in the above question, for example, the velocity can change based on the different masses that you have, right? So you can measure v, and then those are the ones that can be able to change. And then the third thing are constants, right? So under defining the problem, you must have these 3 things. You're writing your question 1 for paper 5. You have to start by defining the problem. What are you even doing, right? I'm trying to change this variable and measure how this variable changes as a result. But I must keep this constant. So what are you keeping constant? A constant is a variable that is kept the same throughout the experiment. Why? To ensure fair test and obtain valid results. If these variables change, they would interfere with the whole experiment. Trick is just to state all the remaining variables or all the remaining constants in order to get all the marks. So if you look at our previous example here, we had multiple variables. We had D, V, M, R, P, G, Q. Some were already told to be constants. But you can see that in this experiment, D and P are variables we didn't talk about, right? We're supposed to then include them. We can just put them down and say, I can keep P and D constant. So it's much easier nowadays because the variables that are kept constant will actually appear in the equation itself. And all you have to do is just look at an equation and extract the variables that you need to be mindful of that. Now, if you do that, you get the first 2 marks under a question 1 for paper 5. You're just defining the problem itself, right? If you want to practice, look at different questions, look at different equations, and try to just identify what is the independent variable, right? What am I changing And as a result, what is going to change? That is the dependent. So you see how easy it is. Just identify, ask yourself critical questions. What is changing? Right? What am I changing? And as a result, what changes? Does that make sense? Right? If anything's unclear on this part, please do put it in the comment section below. So the next part that then follows is method of data collection. So we've talked about method defining the problem, right? So you're going to tell them how are you going to collect data. Now, I highly discourage following this structure where you're like procedure to be followed and you write that as a subtopic, because guess what? The marking scheme really doesn't care about that, right? The examiners are not looking for that. They're looking for your understanding of how you're going to collect the data variables. They're looking for if you can be able to define the problem, right? So if you're writing the structure down, the next part that follows is method of data collection. What goes under here? Under this subtopic for question 1, you must include a diagram as well as methods of measuring the variables that will be present in the equation, right? The trick is to explain how the dependent variable and the independent variable can be measured. What apparatus, what instrument are you going to use to measure the independent and the dependent variable? And also explain how other variables that are appearing in the equation can also be measured, right? This can appear in the additional details, but also just include it under methods of data collection. So let's go through some of the variables that you can tell so that you can be able to tell how to measure this under this subtopic. I'll go through the actual statements that you can write for that quantity. Typically, this part is about 4 to 5 marks, but I highly recommend that you try to include as much as you possibly can. The whole point of the next section is explaining how can you be able to collect data. And as a student, just labeling that. If you're wondering what structure am I going to do, of course you're going to solve past papers, but just know defining the problem, list those 3 things I gave you, and now method of data collection. How are you going to be collecting data? And irregarded, sort of would be covering the procedure to be followed as well as the measurements to be taken, but sort of in a smart, clever way, knowing what Cambridge wants from us. So let's look at some couple of examples. The first one is length, right? So for example, from February March 2024, question paper 5.2, they gave us this road with a length L in that equation. We're not gonna really cover through that a little bit. So you can see I saw L in this question. By just seeing L, I go under method of data collection. I just put a little hash and I'm like, measure L using a meter rule. As simple as that. So measure L using a meter rule is part of the method of data collection. So it's not me saying take take the rod, put it here, take the ruler, place it there. I'm not describing in depth the procedure to be followed like that, like very, very precise. I'm easily just telling them there's L, measure L using a ruler, and I get my mark. Right? The next variable that follows, of course, there are multiple variables. We're just going to go through some of them. Frequency of sound waves or waves in general. The same example from that year, you can see we had F being the frequency. So the frequency is basically the number of complete oscillations per unit time. So we can use a microphone. In this instance, it was sound. We can use a microphone whenever you have sound experiments to detect the sound, and it should be connected to the cathode ray oscilloscope to obtain frequency. So you're going to tell them, use a microphone to detect the sound, connect it to a cathode ray oscilloscope, and then the frequency can be obtained by saying. So you realize that if you look at a cathode ray oscilloscope, you've probably done it in AS or in A2, but basically you're looking at the horizontal length of one wave, right? How long did it take for it to complete one period? Then you multiply that, the horizontal length of one wave, times the time-based setting. What you're getting is the period. The time-based setting is basically how much seconds are represented by each unit division. And if you do that, you're going to get the period, and frequency will be equal to 1 over the period itself, right? So that's basically how you calculate the frequency in that regard. So you're going to need a microphone, you're going to need an oscilloscope, and that is what's going to help you to calculate or to get the frequency, essentially. And this on the side here is an easy drawing setup, right? I'm showing you an oscilloscope and a microphone. So if you're given a question that asks you to measure sound, just draw that when you're drawing the diagram. Of course, we'll cover that a little bit later, but this is just something that you must be mindful of. Another thing you could be asked to measure that could appear under method of data collection is density. Density of a material, right? So you're going to describe how do you calculate density. Number one, you measure the mass using a balance. So you're going to take a balance and you're going to measure the mass that you need to measure. You're going to measure the dimensions of the object if it's a regular object and there's a known formula. And you're going to use a particular method. So for example, if you have a cube, it's going to be length times width times height. If you have a sphere, it's going to be 4 over 3 pi r cubed. If you have a cylinder, it's going to be pi r squared h. And to get the density, divide the two. Just divide the mass with the volume, right? If you have an irregular object, tell them that measure the volume using the displacement method. Take the object, place it in a, a measuring cylinder with water. Look at the displacement, and the difference in that will be the volume of your irregular object. The next variable that we're going to look at is time. An example where this variable appeared was winter 2024, question paper 5.2. And if you look at that equation, you had ATV squared, potential difference V, applied to a particular coil. The temperature increases, and you can see T appearing in that equation. So you can just tell them, measure time using a stopwatch. So the rule is, look at an equation, and from that equation, list all the variables that appear. In that equation, that's T, that's V, that's L, that's M, delta theta. And then tell them how each and every one of those variables can be collected, and you get all the marks and the methods of data collection. As easy as that, guys. You don't have to overthink it and be like, let me write procedure to be followed. Let me explain this. Just list all the variables on the side and tell me, how is this variable calculated? How is this variable calculated? And how is this variable calculated? And you'll be fine. The next variable is probably temperature difference. Using that same example above, whenever temperature appears, you're always going to use a thermometer, right? A simple mercury in glass thermometer that should do the trick, and you'll find the difference delta theta. Potential difference could be another variable you see in an equation. If you just see that, tell them, measure the potential difference using a voltmeter. For questions above, the coil can be connected to an external power supply so that it heats up. Then the potential difference can be measured. And remember, a potential difference is always connected in parallel. And the goal is basically to say, how can I be able to measure the voltage in a particular setup, right? Always connect a voltmeter in parallel, as you can see in the above diagram, right? So if I give you a question, you're going to be able to do that, right? Some questions can have variables that are angles. Look at that equation below, right? My rule is still the same. I look at that equation, I'm like, I have D, I have T, I have theta. So how can I be able to measure each and every one of those variables? And then I'm able to get marks on a method of data collection. So if you ask yourself theta, well, theta, I just use a protractor, right? Protractor, something that helps you measure angles. Next up is frequency of magnetic flux density. So basically, magnetic flux density, you've done it. Magnetic flux is the flow of magnetic field lines. So if you want to measure B, or the frequency of B rather, you're going to have some AC power source. And then if you know the frequency of that AC power source, by default, you've known the frequency of magnetic flux, right? So if you see a question that is magnetic flux, you're going to measure the magnetic flux frequency of that using a cathode ray oscilloscope. Usually when you have frequency, you can easily get away with just using a cathode ray oscilloscope, to be honest, really. Next up is measuring velocity with a light gate. This is very important because there are questions where you have to use a light gate. Let's look at that, or those examples a little bit. So if you're writing notes, I'd highly recommend that you're categorizing every single thing. You started where we started off, and you're putting little subtopic, trying to get nuggets of everything that we're speaking along the way. So draw this little diagram, and I give you this following example. It is given that v, the velocity of this trolley, is related to the angle theta. The velocity v of the trolley can be determined at point x by using a light gate. So basically, what is a light gate? A light gate is sort of something that uses light to measure the amount of time that has been taken for something to move through it. So for example, if you look at that setup, you can have a light gate connected to a data logger. Always say that. Have a light gate that's connected to a data logger so that you can be able to measure the time, right? So how this works is, look at that example, for example, if you have a car, a trolley, you can attach what's known as a card. So just a little card that you put on top of the trolley. So when the thing moves, the trolley moves, it's going to cut the light gate, and it's going to interrupt the beam, and then a circuit is going to go on, and the light gate will start timing the time taken for that thing to move through it, right? If you know the length of the card divided by the time it took for that card to move, you can get the velocity at that point. Does that make sense? So you put a little card on top of your thing, you'll allow it to move down, and the moment it passes through it, you can therefore be able to say the length of that card divided by the time that it took. That is how basically you can be able to use a light gate. But essentially, a light gate will measure the time taken for the car to pass through the beam, and you'll be able to obtain velocity at a particular point by that equation v is equals to L over t. Hope that makes sense. Another variable you might be asked to measure is extension. Again, extension for springs, you just say, for springs, measure the initial length with a ruler. When there's no applied load, of course, apply the load and measure the final length that is present. And extension is basically initial, final length, subtract initial length, right? You're just looking at the difference. How much has this spring extended by? That's basically the calculation, sort of calculation that you'll be trying to make. Another variable that you might be asked to measure is magnetic flux density B, right? Like what I said, is basically the amount of magnetic field passing through an area, a unit area, and it's measured in Tesla. So if I give you an area and allow magnetic field lines to pass, the strength, what measures all of that is the magnetic flux density. It tells you how many of those field lines are passing through that area. It compares the density of those field lines. So I could use a Hall probe. If you haven't seen a Hall probe, look at that diagram at that corner. So basically, a Hall probe is a device that's connected to a voltmeter, and you push it through a magnetic field, and basically you adjust it until maximum value just to make sure it's perpendicular, right? So if you've done magnetic fields, or if you haven't, magnetic fields are maximum, or the maximum magnetic field force rather is experienced when it's perpendicular to the magnetic field, right? So I expect to find the direction in which the Hall probe is perpendicular to the field. Only then can I be able to get the maximum reading possible on this Hall probe. So you keep on turning your Hall probe until you have the maximum reading that will be obtained, right? So you measure, or you can measure B using a Hall probe first in one direction and then in the opposite direction. So then you flip it and you measure it in the opposite direction, and then you average. So you take the two things, you average them, and you can be able to get an average value of B. So you put it in one direction, opposite direction, then you average. These are possibly going to appear under additional details, but these are marks that you put on a method of data collection. And honestly, for other variables, if you know the apparatus that are used in measuring these quantities, it really just be application at that point. The last thing that we're going to cover in this video is measuring pressure or changing pressure, right? For this quantity, we'll use the following paper as an example. Winter 2018, question paper 5.1. I recommend you check that out. So we're given a student that measures how the boiling point of a salt solution varies with pressure. It is suggested that the relationship between Celsius temperature theta at which the water of the solution starts to boil and the air pressure P is given by that equation, where that rho is the density of the solution, K and Q are constants. So you can see that pressure is appearing in that equation, and you have to tell them how you're going to measure that pressure, right? And how are you going to change it? So for pressure, you can use a pressure gauge to measure the pressure, sort of a device that fluctuates whenever pressure changes. And you can also use a manometer, bit of a stretch, wouldn't recommend that, but it's something that you can also use to measure pressure. Then what's known as a vacuum pump sort of sucks air or maintains air in that sense, can be used to then change the pressure, right? I've also included the diagram. You can look at that diagram for that question, and I hope it's really helpful in understanding how to solve the problem as well. But basically for pressure, you can now use a pressure gauge as well as a vacuum pump. So that's basically it, right? Remember, this list is not exhaustive. There are multiple other variables that we haven't covered. It's up to you to look at different papers. Just look at the equation, list the variables on the side, and tell yourself, well, how am I going to measure all of these variables? And put that on a method of data collection, right? Again, let me explain and just summarize what we've done so far. So this is the first part of our question one video series, right? I've introduced what question one is. It's basically a part where you are putting yourself in the shoes of the examiner and telling them how to conduct a particular experiment. You're comparing the relationship between two variables. So when you start this question, if you see the space that says diagram, you see empty lines there. You start by writing defining the problem. So first you have to define the problem in question 1. What's defining the problem? Stating the control variables, stating the independent, the dependent, and constants. Independent variable, what can you change? Dependent variable, what changes as a result? Constant, what are you keeping the same? Put those three down. Constants usually get them from the equation. Pick out all the variables that are left, include them there, or just think at times, what can you keep constant as well, right? After that, method of data collection. Before we do the diagram, I would really highly recommend you first list the method of data collection. I dispute, or I'm highly discourage, saying procedure to be followed, measurements to be taken. That takes a lot of time. And really, all they care, if you look at the marking scheme, is literally defining the problem, method of data collection. And I highly recommend you do that to get maximum marks, right? So under that, you're like, measure this using that. Measure this using that. If there's an equation to include, density is equals to mass over volume. Measure mass using that. Measure volume using that. If it's, for example, Young modulus, for example, stress over strain, measure that using that. Measure that using that. And you write that under method of data collection, you're telling them, for the variables that you gave me, the student should use this to measure that, use this to measure that. And you would have obtained roughly around 6-7 marks, depending on what is contained under method of data collection. That's basically it, right? So if you made it this far, thank you so much. I really hope that it was helpful. And it really helped you in understanding how question 1 can be better attempted. In the next video, we're going to be covering drawing a diagram. How exactly do you even draw a diagram? And I'm going to take you through the whole process of how I think when I'll be solving or when I'll be drawing a diagram, so that I take you through the ideation process and how I'm able to do that. So if you want to check that out, please check out this video, and it will really be helpful in helping you better understand how to solve that. Thank you guys for watching, and I'll see you definitely in the next one.